So welcome back, everybody, to our Gamma seminar. Today we have the pleasure to guest Leonid Ryvkin, who is going to talk about the reduction of multisymplectic observables in our work with Antonio Mitti and Casey Blakey. So, Leo, thanks for accepting our invitation. It's a pleasure to have you here, and we look forward to hearing your talk. So the floor is yours. Please go ahead.
Thank you very much. And of course, thank you very much to the organizers for inviting me and for everybody for coming. So I will report on the work we did together with Casey Blacker and Antonio Mitti. And already the first error in the slides, orders should be alphabetical. Apologies, the technology which worked just a second ago stopped working. Oh, okay. But there is also a second work which we are currently writing up with Antonio, where we understood the same or similar results in a slightly more conceptual way. And this kind of new, not yet published way of understanding them is how I'm going to present them.
Sorry, this one was published in Sigma, yeah?
Yes, it recently came out in Sigma. And I have to be careful with the drawings because they survive slide changes, as I just discovered. Oh, okay. So basically, in the beginning, I'll do a little reminder on symplectic reduction. And within this symplectic reminder, I'll discuss multiple algebraic ways to do it. So we'll start with the Marsden-Weinstein reduction theorem, which is somehow geometric. And then I'll discuss multiple ways how people over the years have done purely algebraic versions of it in the case that things are singular or non-smooth. And then I'll try to kind of explain the subtleties or problems in that. And then the rest of the talk will be how we encountered similar subtleties in the multisymplectic case. Okay, so we'll start with the symplectic manifold. Everything, unless otherwise stated, will be smooth. We take a 2 form, which is closed and non-degenerate. And this will be somehow, if we are from a physical background, cotangent space or something similar as a model of a phase space of a physical system. I already note here that in moral preparation for the multisymplectic part, I'm writing that non-degeneracy is injectivity of the contraction map from the tangent bundle to the cotangent bundle. But because those two vector bundles are of the same dimension, injectivity and bijectivity is the same thing. Okay, so just quickly through the examples. In dimension 2, a symplectic form is nothing other than a volume form. So taking any manifolds with a volume form, like the 2 sphere, the 2 torus, R2, any surface, but not the Klein bottle, gives us a symplectic manifold. Starting from any configuration space, Q, so just any smooth manifold, there is the symplectic structure on the cotangent bundle. And something which gives us a lot of examples are conjoint orbits. Okay, so when we have such a symplectic manifold, we have a way to turn a function into a vector field by taking the differential of the function that gives us a one form. This one form is a section of T star M of the cotangent bundle. And now we just use the fact that contraction into omega was a bijection to invert it and get back a vector field. And this is quite a nice map from the smooth functions to the vector fields, because on the functions we have a Lie bracket, and this map is a Lie algebra homomorphism. So the map is just built by taking the bracket of two functions by inserting the vector fields according to the two functions into the form. Again, a little preview or comment is that here I have two descriptions for the Poisson bracket, and they are the same. However, later when we are in the multisymplectic world, those two formulas will give us two different things. Okay, so the bracket which we just defined on the smooth functions, it's not just a Lie bracket, it's even a Poisson bracket, meaning that the commutative multiplication is derived by the bracket. Okay, now we get to kind of the archetype theorem for reductions, which somehow a lot of reduction intuitions are based on. We take a symplectic manifold, we take a Lie group acting on it, and we also take a moment map, so a map from the manifold to the dual of the Lie algebra of the Lie group which is acting, such that mu is a momentum, meaning that the function which we get from any Lie algebra element by using the mu, its Hamiltonian vector field is the infinitesimal generator of the action. So by we take xi in the Lie algebra, mu xi paired gives us a smooth real valued function. We have just learned those functions have vector fields, and the vector field should be the fundamental field of xi under the action. And then we also require it to be G equivariant, where on the side of G star, we take the co-adjoint action.
Sorry, Leo. Yes,
Yes.
one comment on this condition, because it also appears in your works. Even when the momentum map is not equivariant, sometimes always you can modify the actions on the dual G to make it equivariant. So it's something that people used to assume, but it's in general not necessary. You can do it Marsden-Weinstein reduction without it. So I don't see if you will use really this condition in a way that it's not avoidable. I mean, in the symplectic case, I say, if it's not G equivariant, the usual stuff is to change the Lie group action on the Lie algebra, or even change the Lie algebra G a little bit, extend, and to define a new momentum map that will be.
Mm-hmm. I see. So, I mean, of course, when then the group is compact, you can get equivariance by integrating, and you mean that if it's not compact, you can still do something by extending the Lie algebra, and then the Lie group.
For example, there are several methods to do so. I mean, by means of you can change the action of the Lie group. You can do many other things to avoid this condition.
Mm-hmm. So I think that the way how our main theorem is stated, it will not even require a group action or a momentum. So basically, it will just use somehow the information of what vector fields, so like what is the subset and what are the vector fields. So if one can change anything about the group action to get into a setting where you get an invariant subset and you get a foliation, it will be applicable. So I think it's kind of compatible with those modifications. I'm now just stating somehow the theorem already in the modified way.
Okay, I pick up the point. It's just a comment because there are several conditions that I use. They used to be used in the literature, yeah, and it's become such a kind of I don't know how to say that. Everyone uses, and in certain cases, these conditions are okay. Okay, people are using them because they are quite useful. But in many other cases, you can live without them. And even for certain generalizations, the standard assumptions, they are even annoying. Okay, so it's something also related to works that, for example, you miss in your works. I mean that I read all your works, okay? So I think that there are some missing references and it could be interesting. That's why I'm telling. But the things you
Thanks a
said, they
lot.
are interesting. Yeah.
Yeah,
Okay.
I'll be very glad to add the missing references. Thank you very much. So I think after the talk I'll ask you for them.
Okay, but I think that it's not necessary. But maybe it could be interesting at that point. Thank you. That's all. Thank you.
Yeah, I'll take a comment so I don't I'll take a note so I don't forget it. Okay. Under those conditions, what we get is that in the additional condition that geometrically everything looks fine, which means that at least restricted to the zero level set of the momentum, the action is free and proper. We get the Marsden-Weinstein theorem, which says that we can build a smaller symplectic manifold. So we restrict to the subset, the zero level subset, and we quotient out by the G action. And because the level was because the action was free and proper on the set, we can deduce that 0 was actually even a regular value. So mu minus 1 of 0 is a submanifold. Being if the action is free and proper, the quotienting leaves us to a smooth manifold. And the symplectic thing about this theorem is that actually we can do the same operations to the symplectic form to obtain a symplectic form on the reduced space. Somehow restricting a form to obtain a form is kind of not a big problem, but passing to the quotients needs it to be basic. And one can prove that it is basic. And even more, let's say surprisingly, it will be symplectic, i.e. non-degenerate on the quotient.
May I have a couple of comments, please? Yes. First, for example, you talk about the momentum. First, you assume that the 0 is a regular value. Normally, in the most general case, this is said to be a weak regular value. That is, sometimes it's not as restrictive. And for example, your work, you stated the work by Albert, I guess, about, for example, contact reduction, because you said a lot about different types, and then you will find that normally the only thing they said is that the mu minus 1 must be a manifold, and this is more general than assuming the 0 is a regular value. And the other thing is that, for example, you assume that the action G is free and proper on the level set. And normally they say that they must be quotientable. That means that, that quotient space is a manifold and the project is a summation. So this is the more general stuff. And I have a question for you for what is going to come, because as much as I understood, one of the problems with this thing is the Lie group action on the level set mu minus 1 of 0 doesn't need to be, in many cases, a manifold. Sometimes it's a stratified manifold, sometimes it's an orbifold, sometimes... Well, I have seen lots of structures. So one of your ideas is to make an algebraic approach in such a manner that you skip this part of the problem, yeah? With the part of the structure. So, okay. So thank you. That's what I was interested in.
Yes. So basically, kind of this theorem, I think I'm stating somehow the version which is easiest to state and to describe. And many of the conditions can be weakened. So every time we kind of need something, for example, we use the fact that something is a regular value for the subset to be a submanifold. We could instead, of course, directly ask the subset to be a submanifold. And similarly, for the other conditions, they can be weakened. And I think some of them also, when you want to talk about multisymplectic, need to be weakened, but I'm getting ahead of myself. Okay, so when we look at this procedure, so what we are doing is we are taking a restriction and then we are doing a quotient. And we could look what this means if we pass to the algebras of smooth functions, because somehow one approach one could have is that what matters to us, what is observable. So we just look at the observables in the setting, so the smooth functions. Taking to a subset, restricting to a subset is the same thing on the level of functions as just considering two functions equivalent if they're equal on the subset, which means that the difference is zero on the subset. So algebraically, it's dividing out an ideal in the algebra, the ideal of functions vanishing on the subset we are talking about. And then after that, doing the quotienting bit is actually the same thing as taking the invariants. So we take adjust the functions on this already quotiented space, which are invariant by the induced G action. And now both of these operations are things which need absolutely nothing from which need essentially no conditions. Whenever we have some closed subset, we have the ideal of things vanishing on it. We can quotient it to get observables on essentially any closed subset, even if it's not a manifold. And whenever we have some action which would preserve the subset, we can take invariants to get something which should be the functions on the quotient. And this will be this somehow the guiding idea or spirit of the talk. Instead of doing things on the geometric side, we are just working with the function algebras. When we want to talk about their vector fields, we'll talk about their derivations and so on. So we translate to algebra, and their regularity assumptions become less relevant.
Yeah, just one comment, because I agree this is interesting what you are doing, but just a stupid mathematical remark. But sometimes when S is just a subset, you have to talk about if smooth function on S is a little bit abuse of notation. Yeah, I understand the point, but S can be whatever. So it does not need to have a manifold structure, or it will be difficult to say how these functions are smooth with respect to, yeah? Or
Yes,
you have an idea?
So this is somehow just a definition. And in the case where S is some smooth sub-object, it will give us the thing we want. But yeah, so I mean, in this context, smooth is just a name. However, there are works of Whitney who discusses smooth functions on closed subsets, and he defines them slightly differently. And then it's a theorem that it's exactly the functions which are restrictions of smooth functions on the whole manifold. And then this becomes somehow, this definition becomes a theorem.
Right, because indeed this was I was expecting, kind of. But who said who did that? I didn't.
I think it's Whitney.
Okay,
Yes.
so I will. It would be nice to take a look. Thank you.
Okay, in this diagram, there is one thing which will somehow make things conceptually a little bit less nice to work with, which is that before we did a restriction and then a quotient, and now we are doing a quotient and then a restriction. And it's like there is no big conceptual problem with that. It's just that for the framework we'll work in, it would be nicer to always talk about subset and then quotient. So this diagram we can rewrite also into restriction and then quotienting, just by first restricting to the functions whose restrictions to the subset are G invariant. There is a symbol which moved to a wrong place, so the what are we doing? So functions which are smooth such that the restrictions to S is G invariant. And then after that, we quotient by the same ideal, and it's a calculation that somehow doing it in this order gives us the same space as before. And now we are restriction and then quotient as before. And we will phrase everything we do in this restriction and then quotient spirit. Okay, so there is one problem with this procedure at the moment we are kind of giving up on the conditions of the Marsden-Weinstein theorem. Marsden-Weinstein theorem. It's that this does not in general give us a Poisson algebra. And there is one approach to resolve it. So the problem is in Dirac's language that not all constraints are first class. I'm not going to go into that. I just wanted to note that it's somehow understood why this is a problem. But one thing which one can do is to look at different quotienting procedures. So the one we have just seen is we take those functions who are G-invariant on S and quotienting them by the ideal. But something else which one could do is taking just the functions which preserve the ideal IS. And if IS is in it, then quotient Fs by IS. So this is somehow this Dirac approach. But other things you could do is you could just look at the invariant functions and quotient that by the invariant functions vanishing on the subset. Or what you could do is you could look at the invariant functions and quotient by the functions which are G-invariant, but which are also generated by the momentum. So now we are kind of reintroducing the momentum. We can use the momentum to construct an ideal, which is just basically smooth functions multiplied with components of the momentum, finite sums of those. This in general is not the same thing as IS. In the regular case it is. So this is not equal to IS. It is in general. But it's always a subset. And or something else which we could do is we could take the normalizer of this ideal I mu and divide it by I mu. Or what we and those are somehow all different reductions for the singular symplectic case present in the literature. So the first thing, as I said, because it's not giving a Poisson algebra, I would call it naive. This is somehow observed by Dirac, who repaired it by the second approach. The third one is from a paper of Sniatitsky. The fourth one from a paper by Arms, Cushman-Gauthier. And the fourth one by a paper from Sniatitsky-Weinstein.
Yes, just one thing. Sorry, one question. There's the condition, the ideal IS is included in Fs is what's in the standard differential geometric case is the coisotropy condition, yeah? Because
yes.
Yeah, okay. Thank you.
And yeah, so we have like already a large amount of different things to do, and it's in some sense so there are theorems when they coincide, when they are really different, etc. And basically what we can do is, even in the symplectic case, we can propose another one, which is the one which appears if we plug in a symplectic manifold into multisymplectic reduction.
Sorry, may I have another
Yes.
question? One
Yes.
second. The I mu you define it as a linear combination with the functions of I with the coordinates of the momentum map. Yeah.
Yes.
Why a linear combination exactly? Why? Because you could do it more general. I know that this is related to, I think that it was Sniatetsky, yeah, work. But I found that in some cases, some results can be done for more general types of I mu. Why it's the linear combination? Could you comment on this fact, or which is the problem? Which is the sense of this?
So basically, your is your question rather why are we not taking more, or why are we not taking less?
Both things. I mean, I found
Okay.
that several results are for more and other for less, but you can comment why this exactly, because when you see this for the first time, you see that everything works, but one has no idea, or at least I have no idea why it should be like that exactly, or why it's going to be like that. So it could be a nice to know some comment on it, please.
Mhm. So I think that one doesn't take anything smaller because this I mu is the smallest ideal which contains the components of mu. So
Mhm.
so
Yeah, yeah.
so if we really want somehow to model something which is mu equals to zero in an algebraic way, then we certainly want the components of mu to be in it. And then if we take the smallest ideal that contains them, this is what we will get. Um, so we could take bigger things, and it is possible for it to be in a setting where taking IMU doesn't lead to a nice space, but taking something bigger would lead to a nice space. So it
Mhm.
can be a good choice. However, in principle, because we're taking the smallest space, in some sense, we are guarding as much information as possible. So basically, if our mu is something like um, just one coordinate and it's somehow some function x to the power of 4. Then this IMU ideal will completely remember this order of vanishing. If we, for example, would take the radical ideal,
Okay.
we would
I become,
not see
yeah,
that.
I see it now. Okay, right.
Oh, okay. Um, so yes, just a remark that somehow those places which which I called NU, if the group is connected, the letter N becomes justified in the sense that it becomes the normalizer in the Lie sense. And in the sequel, when we work algebraically, I'll only work with connected groups, so I can give nice infinitesimal descriptions of what is going on. Okay, so basically, this is in some sense a teaser for the very end of the talk. Um, when we develop the theory of multisymplectic reduction, and then we apply it to symplectic, we get this slightly more complicated space, which could be seen a little bit as a mix of the previous ones. So we have somehow this ideal IMU that we had just seen. We are somehow only recovering its first order information because we are adding the space of all functions that vanish on S and whose derivative vanishes on S. So those are functions which vanish quadratically on the subsets. And then somehow in the numerator, we are doing the normalizing to this, I don't know, linear information of mu. And we are also normalizing the full ideal IS and taking the intersection of the two. And this kind of, at first sight, at least to me, looks quite arbitrary. But the two components will, in the very end, come from the fact that we want to preserve not only the function, but also its Hamiltonian vector field. And this is somehow what the two components will be responsible for. Okay, so uh, here now this is somehow maybe answering partially your question about generality. Um, we can do this extremely generally for any Poisson algebra with two ideals, um, one of which is a Poisson ideal, and the other one is preserved by this Poisson ideal. So the I would be the I mu, and the J would be the IS. And the IS in general is not the Poisson ideal, but the IMU is. And moreover, one can show that IMU preserves IS. And this is somehow, for the algebraic procedure, the most general setting where it works.
Have you
Okay.
tried, sorry, have you tried to check what this means geometrically?
In some sense, the way we got to this formula is through trying to do something geometrical. So I hope that at the end, the answer will be yes.
Oh, well, wonderful. Thank
Okay. I don't remember what the formal length of the talk is.
you. 1 hour, but
Oh,
it hardly ever takes 1 hour. Indeed, I will at 30 moment receive an WhatsApp from my collaborators telling Javi is up and let the speaker talk. So let
okay.
us say that formally is 1 hour. Okay, you can take something 10 minutes or more like that. Eventually, we can discuss a little bit by ourselves. So
Okay.
16, 15 is okay. 10, 15. Okay, more is impossible
Okay.
because of lecture.
Okay. Thank you. Good. So now this was somehow the symplectic case. Now we're going to the multisymplectic one, which was our actual motivation of work. And this multisymplectic manifold is a symplectic manifold where we are forgetting about the fact that the form has to be a two-form. We are now suddenly allowing forms of arbitrary degree. And then suddenly saying that omega flat is injective stops being the same thing as saying that it is surjective. So in most cases we'll look at, it will be injective but non-surjective. And also, because we're working algebraically, a lot of what we are doing does not need non-degeneracy. And even when non-degeneracy is there, the procedures don't preserve non-degeneracy. So we would be in sort of a pre-multisymplectic case. Okay, again, quickly going through a list of examples. The same way how oriented two manifolds are symplectic, any orientable manifold is multisymplectic when equipped with a volume form. And the volume form case is a case where, again, injectivity of omega flat is equal, the same thing as surjectivity, and symplectic and volume are the only two cases where this happens. The example of the cotangent bundle can be generalized to a multi-cotangent bundle. The same way one has somehow a canonical n form on lambda n t star q, and its exterior derivative turns out to be multisymplectic. And somehow, in spirit replacing coadjoint orbits example, one can look at multisymplectic three forms on semi-simple Lie groups, and then there are further examples, hyperkähler manifolds, and so on. In general, it is relatively easy to be multisymplectic. So unlike symplectic, where there are topological obstructions, typically in multisymplectic, you don't have them. You give me an arbitrary manifold and a K, which is somehow like a degree, which is not volume and not symplectic, but somewhere in the middle, and then one can find a multisymplectic form on it. Okay, so what I want to do is I want to describe the observables in the multisymplectic case, but to do that, I'll motivate them back in the symplectic case in a certain way. So we go to the simplest symplectic case we can imagine, except points, which is we take a two-dimensional manifold, standard volume form, and we look at the space of vector fields which preserve it. When we want to understand those vector fields, we notice that, okay, preserving omega is it's a kind of not super easy condition. What would be easier is to just look at functions which induce such vector fields. There is a way how any function does. It's exactly this f goes to xf we had before, which one could call symplectic gradient. And one defines the Lie bracket on the functions, which is compatible with the symplectic gradient. And now we can say, okay, this was quite a successful strategy. Instead of working on the slightly more complicated space of vector fields preserving a form, we work on the space of all functions. Let's try to do this in R3. So we take all vector fields on R3. We take a standard volume form. We now want to look at the volume preserving vector fields. So divergence-free vector fields. We do have a function, the curl or the rotational, which gives us all volume preserving vector fields in this case. However, if we look at the Lie bracket on the left and the Lie bracket on the right, they don't coincide. However, on the left-hand side, we can define a new better bracket, which is compatible with the Rod map. So the new bracket, which we use the curly brackets for, is mapped by a Rod to the bracket of the individual components. However, if we compute for this new bracket the Jacobi identity, we don't get 0, but we get a gradient of something. And this is somehow the whole spirit of this multisymplectic Lie-infinity algebras. Instead of quotienting out all total divergences, which would lead to a complicated space, we stay on the nicer spaces, but we live with the fact that Jacobi holds only up to something, and we carry along this something in our data. So in total, what we have is we take the domain for the Rod, the vector fields on R3. We take the thing where the correction terms has come from, which was a smooth functions, and we equip them with a bunch of brackets. So the first bracket is the gradient, the second bracket is the curly bracket we have just defined, and the third bracket is the correction term, which corrects the Jacobi identity. And they form an Lie-infinity algebra, which basically means a bunch of identities of what happens when we apply one bracket after the other.
Sorry, Leo.
Yes.
Some people call this term the magnetic term, or the in multisymplectic geometry. Yeah,
Manetti
because you
term.
don't. Yeah, the magnetic term. I saw
Magnetic.
it a couple of times. Yeah, the Jacobi identity does not hold. There is up to a term. Yeah, and you want to control this that the normal is closed and in the multisymplectic setting. Yeah.
Oh, I haven't heard that yet. That's very nice. Thank you. Good to know.
Thank you.
So I'm not writing down the equalities a general Lie-infinity algebra is going to satisfy because it's somehow a little bit too many signs. But in our case, we somehow have a relatively mild version of an Lie-infinity algebra. Our binary bracket disappears on the image of L1, and the Jacobi that identity holds up to L1 of something, and this something itself satisfies a sort of Chevalier-Eilenberg differential type identity itself. And if we were in R4, this last 0 would become L1 of L4, and there would be a next term. So I think I don't know how familiar the audience is with Lie-infinity algebras, but I think because we're going to next look at basically the abstract version of this, so maybe on this concrete level, I'll be glad to answer questions or take more comments.
Most of people in here, I think that they are not familiar with infinite algebras. In my case, I am, but if you can skip the more technical parts about that, it could be nice for everybody, I guess.
Okay, so yeah, I just somehow the important thing is the basic idea is we have the vector fields and they don't quite form a Lie algebra, but the degree to which they don't form a Lie algebra is measured by a smooth function, and we have somehow the algebraic structure to encode this with those unary bracket L1, which is just the gradient, binary bracket, ternary bracket, etc. Okay, so this is the slide with the general definition of what we would get in Rn or in general, or even more generally on any pre-multisymplectic manifold. There are so the first thing is that we used to have the association which somehow from F brings us XF. And when we are non-degenerate, this is, whenever it exists, unique. I mean, now we are in multisymplectic, so the F is actually a differential form, so we would have alpha and X alpha. But in much of what we do, we will not be able to find a unique X alpha for a given alpha. So so we are just carrying it along in our definition. So we have here that the Hamiltonian pairs are pairs of a vector field and a form. And we want them to satisfy somehow the Hamiltonian equation. Contracting the vector field into omega up to sign gives us d of the form. And whenever we are in the multisymplectic case, we can kind of forget about the vector field and completely reconstruct it from the form part, but we don't assume that. So this is what would have been in the R2 case, just C infinity of M. And in the R3 case, it would be vector fields on M. Oh, here it's not visible. Okay. Vector fields on M. And actually, the better way to think about those vector fields, which we would have in the R3 case, it would be that they are one forms. And somehow, when we would go higher in the dimension, we would have K forms, but we wouldn't have all of them, just those which satisfy the Hamiltonian condition. Now we have, in general dimension, we have more correction terms, which are just given by the lower part of the de Rham complex. And the L1 will just be the de Rham differential. And the higher brackets are all of the same building type. We start with Hamiltonian pairs, alpha 1 v1 to alpha k vk. And we just plug all the vector fields into omega and decorate it with an appropriate sign. And on the L2 case, because we have wanted to be in the presetting, we have to carry along what the vector field is. And on the vector field level, it's just the commutator as we wanted to. So maybe as an image for it, we have a chain complex, the de Rham complex. On the last level, I wrote Ham0 because it's not just the forms, it's also some vector fields, the components. And then we have a binary bracket taking two Hamiltonian forms to 1. And then there is a ternary bracket, which is taking two k forms to 1k minus 1, sorry, 3k forms to 1k minus 1 form, a 4 bracket, a 5 bracket, and so on, up until one arrives at C infinity of M. Okay, so the abstract statement is that this is an L-infinity algebra, which means that when we apply L1 to a bracket, it's the same thing as applying the previous bracket kind of in all multiple configurations where we put the commutator into the first slot. It's essentially the definition one would get in a Chevalier-Eilenberg cohomology of a Lie algebra. And this is one choice one can take. The other choice would be the non-skew symmetric choice, where one doesn't need correction terms. So somehow the spirit we are going to follow, it will be mostly the L-infinity spirit, which is that we keep skew symmetry, but we lose Jacobi, so we have correction terms. But there is an alternative one, which is we lose skew symmetry. We define a bracket on the forms which is non-skew symmetric, and we don't need correction terms. This is what would be called the Leibniz algebra structure.
This recalls a little bit what happens with Dirac geometry, with the Dorfman current approaches, yeah? I think in one case you have some kind of line of Jacobi identity, but it's not antisymmetric, and the other way around, yeah?
Yes, exactly. It's the same phenomenon, absolutely.
Yeah, okay.
Okay. So one remark is that this construction, how we get the L-infinity algebra, can be done to any Lie-Reinhardt algebra. So a Lie-Reinhardt algebra is an associative algebra plus a Lie algebra, which is also a module under the associative algebra, such that the bracket acts as derivations. It will appear a little bit later, but yeah, the identities are already written here. So we have a commutative algebra, or it won't even just be associated, but even commutative. We have a module over it. The module is a Lie algebra, and the Lie algebra knows how to derive uh, elements of A, and we satisfy Leibniz identity with respect to that. Okay, so now we come to to our objective. We want to do reduction in the multisymplectic setting, but we want to do it in an algebraic way. So we start with our Hamiltonian Lie-infinity algebra. We want to find a subalgebra of it and an ideal, and then we quotient the subalgebra by the ideal to obtain a new L-infinity algebra, which we will see as the reduced one. This idea of triples, algebra, subalgebra, ideal, while kind of course, around in reduction as an idea everywhere, it has been formalized in the PhD of Marvin Dippel, who called such triples constraint triples. And he has constructed a very elaborate algebraic theory of them. So we know what constraint algebras are, constraint modules, constraint tensor products, constraint derivations, etc. And basically, more or less at the same time as he was developing the algebraic theory, we found this multisymplectic observable reduction by hand. And after that, when we met and discussed, found out that it fits into the framework developed by him. And I'm going to present it to some extent in terms of this framework. So before we had the constraint triple C infinity of M, for example, C infinity of M is. So when we just want to describe the quotient, the algebra and the subalgebra are equal, and the thing we quotient by is the ideal is. And it forms a strong constraint algebra in the sense that the ideal is, it's not only an ideal in the subalgebra, but also in the global algebra. So this is something which is called strong in this context, where our equivalence relation is not only defined on our subset, but on the whole ambient set, which will be the case for example, group actions on a manifold. We don't just have a group action on the zero momentum set, but on the whole manifold. So maybe the remaining notations of the slide, we will call the global algebra AT, total space, the subalgebra AN, normal space, and the ideal A0 for the zero space. Okay, so as we have said, total space will be algebra of smooth functions. When we want to talk about vector fields, those are just derivations. The closed subset we translate to the ideals of functions vanishing on it. And when we have an action, we can see its infinitesimal part as just the derivations it generates. So we will, for now, we will omit the fact that non-connected groups exist and work with connected ones. We will identify an action with its infinitesimal action. And then we need something to say that the G action preserves the subset S. And we will just write it down algebraically so that the fundamental fields of the action preserve the ideal. And here is somehow the first big warning that in general, we are not replacing a notion with an equivalent one yet. So algebraically speaking, the vector field dx preserves the closed interval 0, 1. But if we look at it geometrically, the flow of dx, of course, moves out of 0, 1. So this condition is weaker in the algebraic setting than it would be geometrically. Okay, so now we have our algebra, and we had recently said that to do an observable algebra, we need a Lie-Reinhardt algebra. So we need the algebra, its derivations, and we will also need the multisymplectic form, which will just be a cocycle. So let's turn to derivations. The same way how the algebra was a triple, the derivations will be a triple, with total space being all derivations and normal space being the derivations which preserve both the normal and the zero space. So because an and at are the same thing, the first condition, v of an is in an, is not really there. And a0 was the ideal is. So preserving a0 just means that we are preserving is. So it just means that our vector fields are algebraically tangent to S. And the zeros part, so the type of vector fields which we shouldn't see in the quotient, which are become invisible, are the vector fields which map anything to is. So whatever function you start with, the resulting function will vanish on S, and those are just the vector fields vanishing on the subset. So the subtlety which we saw on the previous slide with the normal part, so that being tangent algebraically is weaker than being tangent geometrically, it doesn't appear on the vanishing part. There, geometric and algebraic vanishing are equal. Okay. So, and now comes kind of an algebraic theorem, which is somehow a long list of properties to check. It's the fact that those derivations, they form a constrained Lie-Reinhardt algebra. So they form a Lie-Reinhardt algebra. It's this associative commutative algebra plus a module over it, which is a Lie algebra with certain conditions. And all those structures preserve this triple total normal zero. So when we multiply something with a zero, it automatically is in L0. If we multiply L0 with anything, it's in L0, etc. We have a whole list of compatibility conditions which are satisfied by the derivations. What this implies automatically is that when we build a Cartan calculus from this, the operations of Cartan calculus, meaning total derivative, interior product, Lie derivative, they are all compatible in a certain sense. So we have a constrained Cartan calculus where the total space will just be differential forms on the manifold. The normal space are those forms which, when we only put in vector fields which are tangent to S, give us something in an. Okay, so the first one again is not a condition. And when we pick all of them tangent and one of them even vanishing on S, then we want to get something zero on S. And the zero space, the forms which we don't see, are those which are just always zero on our subspace. Okay, so what we have seen so far was just working with a closed subset. We haven't yet introduced the G action, or like the symmetry which we actually wanted. So let's do this now. We take any subset of the symmetries, of the derivations which are algebraically tangent to our subset. Typically, this will come from a Lie algebra action, but this is absolutely unnecessary for the construction. And we built a new constraint algebra. So again, as a total space, we take all functions. As the vanishing space, we take the subset S. And as the normal space, the things we want to look at are those things which are invariant on S, which kind of means that if we apply a derivation, so apply something from our symmetries, then at least on S, we don't see anything. We can now, with the introduced symmetry, introduce a constraint Lie-Reinhardt algebra. So instead of having all vector fields tangent to S and all vector fields vanishing on S, we are looking at smaller spaces. The vanishing part is more is somehow the more intuitive one maybe to start with. we take the symmetries which we introduced, and we take the smallest Lie-Reinhardt algebra containing them. So this is a little bit like getting the ideal I mu from I. It's just the smallest thing. Taking C infinity linear combination has to be allowed. And then what we add to it is everything vanishing on S. And the reason is that what we want to do with the quotienting procedure is we want to see things on S. We want to see vector fields on S. So we divide out everything which is localized away from S. And now on the middle part, we are looking at a sort of normalizer of the space. We are looking at the vector fields, which when we apply something from F to them, we land in this invisible subspace. I should say that here instead of F, we could take C infinity MF plus ISXM. So like this is just to write the condition in a shorter way, but in principle, the idea is that this is what is invisible, and when we apply a symmetry to something which is invisible, it should stay invisible. Okay. So now we can look at, so now we have the algebra, we have the derivations. To build the multisymplectic Lie-infinity algebra, we also need the differential forms. And here what we do is we take the differential forms which are basic. And being basic means that contracting a symmetry into them or doing a linear derivative vanishes. But for us, vanishes means it vanishes on S. So in the algebraic sense, so this is the condition we impose, that iota psi alpha and L psi alpha are in the zero space, in the invisible space from before. So this gives us a new version of the de Rham complex, again with the triple, total, normal, and zero. We have the Lie algebra, Lie-Reinhardt algebra we look at with total, normal, and zero part. And those have a Cartan calculus together, which means that the construction we saw earlier, which just used Lie derivatives, interior contractions, and total differentials to build an Lie-infinity algebra, we can just carry it over. And this is somehow what our reduction construction is about. We identify a subalgebra of the multisymplectic Lie-infinity algebra, and an ideal we can quotient out of it to get a new Lie-infinity algebra, which we call reduction. So
sorry, Leo, yes, one piece of information. Maybe you have still 10 minutes till the end, okay, because we cannot extend, at least for a student.
Yeah, of course. I think that this is this is the point I wanted certainly to get to, and after that I'm going to just do two remarks, and then we can turn to the discussion. So I think I'll just go explain the pieces here, because this is somehow answering the question of what does the algebraic stuff mean geometrically. So our reduced Lie-infinity algebra, it has, so in most degrees it's just a differential form, in the lowest degrees it's a couple of a form and a vector field. So if we're just on the form part, what we want is a form on the quotient, which means that it's a basic form. It's a basic form, those are those two conditions. And we identify two such forms if they are vanishing on the quotient. So this is this is this condition. When we are on couples of form and vector field, then additional conditions join. So first of all, of course, we want the form and the vector field to be compatible. Then we want it to be the vector field to be tangent to the subspace, and then we want the symmetries to preserve it, and preserve it in the right sense, meaning that applying the Lie derivative to a symmetry gives us a symmetry, at least when restricting to S. So this is somehow, so long calculation involving constraint Lie-Reinhardt algebras yields, this is an L-infinity algebra. So the top is an L-infinity subalgebra, the bottom is an L-infinity ideal. The quotient will be an L-infinity algebra, and this is what we would call reduction.
Sorry, have you think about using a higher Dirac structures? Because many of the things you have been using there look very similar to third-time structures using in there.
We haven't yet looked at that. No, thanks a lot. I'll take a note. Version. No, so yeah, I cannot right away say anything very competent about it. My feeling is that if there is some algebraic procedure for the reduction of Dirac structures, it has high chances of fitting into the framework because we are really just kind of keeping track of what is divided out and what is tangent to a subset.
Yeah,
That's very general.
I guess, but you know, geometrically and somehow all these structures, these vector fields with forms and higher order, these, for example, some of the conditions in here are the straightforward analogous to the higher order derived structure, what happens with derived structures in the symplectic setting. And I don't know how much this could work or how you could translate, but in certain cases, it could be an interesting approach. And much of the things you are doing in here with this alpha, for example, being that it is projectable and things of the sort, they used to appear in third-time reduction procedures for Dirac geometry. Indeed, the questions you did at the beginning, it also recalls me certain things, but it's something that should take a look at. I mean, it's the feeling one has, okay? I don't know how much this could work.
No, that sounds very plausible. Thanks a lot. Yeah, I'll have a look. Interesting. So I'll maybe just remark that multisymplectic moments. So give us an example for it, but we need to use the Leibniz structure for the moment for this to work. And this is what geometrically was done by Casey Blacker. So Casey has reduced multisymplectic structures in the presence of a Leibniz type momentum map. And so there are two things. First of all, he obtained something which is only pre-symplectic, even if he starts pre-multisymplectic, even if he starts multisymplectically. This is why we are always dragging along the vector field by hand, because non-degeneracy is not preserved by the procedure, even in the best cases. And the second thing is that unlike the symplectic case, reduction doesn't see everything in the multisymplectic one. So I'll just leave the full slide. So we have from our reduction, so this is the thing on the left, to a geometric multisymplectic reduction, an injective map. Everything is constructed such that in the smooth case, we recover forms which pass to the quotients, vector fields that pass to the quotients. But in the general multisymplectic case, this map is not surjective. So there are observables on the quotient which don't come from the original space. And the reason is that being Hamiltonian can be very difficult. There can be some very complicated condition, which is simplified when you take a subset or quotient out of symmetry. And so basically, maybe the upshot, if we forget all the technical bits of the talk, is that even when you want to reduce multisymplectic Lie-infinity algebras, you still need rather a Leibniz algebra momentum and not an L-infinity momentum. And the second observation is that one should not expect every observable on the reduction to come from an observable on the total space. And I think this is a nice point to stop, and we can continue more in the discussion format during which people can leave.
Okay, so thank you, Leo, for your talk. So let us say, is there any question, remark, Leo? Well, I think that it's we can finish here for students. So thank you very much.
Yeah, sorry,
Leo.
maybe one short question. I mean, could you comment
sure.
on on relation with weak homotopy momentum maps or just homotopy momentum maps?
Yes. So this is in some sense the if you're an L-infinity person like me, slightly disappointing fact that we need Leibniz momentum maps for this to work. So if we try to do this procedure with the homotopy momentum maps, it doesn't really work, at least so far. And it feels like having actually a subset, which is the zero momentum set, and not somehow a subset up to homotopy, whatever that means. Kind of that then weak momentum maps or even homotopy momentum maps become a too flexible notion that they don't really the things which we need to preserve to do the reduction are not preserved. There is work by Christian Blomann and his student PhD student Janina, and I unfortunately forgot the surname. I can look it up. Who have started on looking on multisymplectic reductions, where they are actually looking at a zero locus in a homotopy sense, and in this zero locus in the homotopy sense case, the multisymplectic homotopy momentum map seems to be the better or a good object to use.
Okay, thank you.
No, yes, just one question, because I don't know if sometimes you said one thing and then the other. I didn't understand. I mean, your when you start with a multisymplectic structure with one with the non-degenerate, yeah, does please make it clear, does your procedure conserve the fact that it's non-degenerate?
No, it does not.
Does not. Okay.
And
do you have any hint?
Like an example, you mean?
No, example. There are lots of examples. I mean, what do you have any hint to know or how to look after this fact? I mean that you have a multisymplectic form. I mean, I know degenerate. Do you have any idea how control if it will be non-degenerate on the reduced space?
Okay, I see. Well, how a way to control it. I would suppose that you cannot expect to have any general sort of theorem, because multisymplectic manifolds, they don't have Darboux theorems. So
Yeah,
I think the thing which is somehow rescuing the symplectic case is that you have this local normal form, and you kind of know that every coordinate has its partner, and that if you're quotienting out one coordinate, then you are restricting to the subset where the other one is zero. And so I would think that what you could try to do is look at manifolds with some fixed local normal form. So I don't know, for example, the multi-cotangent spaces do have such a normal form. And there, if you know that, I don't know, your symmetry is only involving vertical coordinates. Plus,
I pick up the point. So it's much. I was thinking if you had something I could use, but what you are telling me is more or less what I thought at the beginning. So, okay, so thank you very much, Lodi, and thank you for making clear this point, because for mathematicians, they look for something similar to the isotropic conditions, yeah, the algebra isotropic condition for symplectic. But the problem is that the multisymplectic doesn't work. Physicists, let us say, they don't much care about non-degenerate multisymplectic forms, let us say this way, because most models are degenerate and they don't care much about it. So for them, it's a little bit of a kind of artificial problem, yeah. And indeed, we have in my department one of the guys who developed multisymplectic geometry. We have Kijowski, was one of the first one, and also you can ask him, but what he will tell you is that everything that it was worthy, we did it, and we don't believe in it anymore. They think that the multisymplectic thing in physics is. You can ask him, okay? He will tell you exactly that. And we had also Tultiev, yeah, that we used this. Well, we know that Tultiev wrote things very carefully and worked on the topic. But any of them, they are convinced on it. But it's a problem for mathematicians, they say so far. We had Luca Pitagliano also with multisymplectic geometry some time ago, and he said what he said. He's very nice. He doesn't try to make you feel uncomfortable or nothing. It's something to say. I don't believe that in physics anything of this will be worth it anymore. But he really believes it. Okay, it's something like it's fun being here and talking about that. Okay, so thank you. We can finish because 4:15 people are leaving and they have to go to the following lectures and things like that. Some case. So thank you, Leo, for your talk, and we can talk still for a while if you don't mind. But just for those who want to.
Thanks a lot. Yes, and yeah, thanks a lot for the invitation and for staying here.
Yeah, sure.
Well,
Thanks
thank you, Leo. Just let me say that since we are saying goodbye to almost everyone, next week we will have Anna Balibanu from the Louisiana State University, and we'll talk about reduction along strong Dirac maps. So we will continue with these reduction talks next week. So thank you all for attending and see you next week.